Okay, so it is, well, 11:30 in my time zone. So let's get started. This is session 4B of Sazerac. I'm Charlotte Mason. I'm going to be chairing this session. So just a couple of reminders. First of all, please continue asking questions in Slack. And I definitely encourage you to ask questions during the talk as well. Don't just wait until the end. And obviously, of course, you can remember to like the questions too, so we can see the sort of highly rated questions to ask during the talks. So our first talk today is from Axel Runnholm, who's going to tell us about using Lyman Alpha to constrain the progress of reionization.
Okay, thank you very much for letting me speak at this conference. It's been very nice so far. Yeah, I'm going to talk about how we can use Lyman Alpha to observations at low redshift, specifically to constrain reionization at high redshift. So just starting from the beginning, why should we, or can we even use Lyman Alpha? Well, Lyman Alpha is an intrinsically very bright spectral line, and this is obviously very useful because it makes it much, much easier to detect at high redshifts and towards the end of the epoch of reionization. But it's not just bright, it also is resonant, which means that it interacts with neutral hydrogen in the IgM. And it hits optical depths of 1 at very low H1 columns. And what this means is that the IgM neutral fraction will suppress Lyman Alpha. And we should be able to see that suppression. Okay, so then the follow-up question is, what's the problem? This should be easy. Well, the same thing that makes Lyman Alpha useful for studying reionization is also what makes it hard, because the resonant nature of the line means it undergoes a lot of radiative transport within the galaxy itself, within the ISM, and understanding Lyman Alpha output then becomes much more complicated. And when we look at low redshift galaxies, we see, or galaxies in general, we see a large variance of the amount of Lyman Alpha that is escaping, both in luminosities and in escape fractions. So the problem becomes trying to decouple the ISM and the IgM, and that turns out to be very difficult. So if the ISM is doing so much Lyman Alpha, how can we tell what is caused by the IgM? So what I will present is our project to try to understand the ISM part of it, and how Lyman Alpha escapes from local galaxies. So we use a sample of galaxies called LARS, or the Lyman Alpha reference sample. And it's a sample of 42 nearby star-forming galaxies where we have Lyman Alpha in imaging from HST. And we also, and I mean, they're low redshift galaxies, so we don't have to worry about IgM absorbing any of this Lyman Alpha, so we can really focus and understand the ISM component. And they're also close by enough that we can get very detailed data sets. So we have data sets that include Lyman Alpha imaging, far UV, H alpha, etc., as well as UV spectroscopy. So what we do is we take all of this data and we split it into two sets of data that we want to look at separately. And one is direct observables, so far UV, H alpha, H beta, that sort of thing. And the other is just derived physical quantities. And what we want to do is to then understand how we can predict Lyman Alpha or understand Lyman Alpha based on all of these other quantities. We had a bit of an introduction to this biomopia in the last session, which was very nice. But what we want to do is combine many sources of information. but this can obviously be done in some very many ways. And but because we only have 42 galaxies, we really want to try to keep the model itself simple. So we do multivariate linear regression, which essentially becomes fitting a very multidimensional plane to this and trying to derive a predictive relation for Lyman alpha from this. So when we do this, we then predict our Lyman alpha luminosities. We get these results. So what we're seeing here on the y-axis is the observed Lyman alpha luminosity. And on the x-axis is the prediction from our regression model. And we see that we get quite nice predictions. The left column shows the regression model based on physical variables, so star formation rates, dust extinction, that sort of thing. And there we predict 85% of the variance in the sample. And if we go to the observables, so far UV and things like that, we get up to 93% of the variance in the sample in our models. So if you're used to looking at single correlations of Lyman alpha against something else, these ones look quite nice. But a model that predicts something very well, as long as you've fitted your model to that data, is not very useful. We need the model to generalize outside of our data as well in order to be useful for anything, really. And we were fortunate enough to be able to gather together data from a number of other galaxies that were not in the LARs and try to put together a reference sample that we can test our prediction on. This was based on galaxies in Yang et al. 2017. And here we see that result. So we have our relation that is fitted only to the orange and black points in this figure. And then we have the squares that are predicted from our relation. And what we can see is that we actually generalize quite well. We see that there is a bit of a skew, but that this also is proportional to the redshift of those other galaxies. And we believe that this is aperture effects, because the Lyman alpha in these reference points doesn't come from imaging, it comes from COS spectroscopy, which has a much, much smaller aperture. So we think that this model actually generalizes really well. And this, if this holds true, this really does enable us to look at the IgM opacity and things like this, because if we can predict the intrinsic Lyman alpha before IgM attenuation of high redshift galaxies, and we can observe Lyman alpha, as we have seen throughout many sessions today and yesterday, we can look at the difference between these two quantities, and that should be due to the IgM opacity. The problem is that getting enough data to do these relations will require next generation telescopes, so JWST for H-alpha and ELTs for UV spectroscopy. But we can also see the impact of IgM if we look at Lyman alpha spectroscopy. So local galaxies, like the one shown here, often show a blue peak in Lyman alpha emission. And this blue peak is expected to be suppressed first. So this is the galaxy at redshift 0.3, but if we attenuate it by expected IgM at various redshifts, we see that the blue peak shrinks down very quickly. And there is a sample of Lyman alpha spectra across this redshift range from the Muse-wide. They've released over 500 spectra. And in the individual Muse-wide spectra, we can't see any blue emission, but if we stack them, we can. And if we stack them by redshift, we can see the evolution of that blue peak contribution. So if we look at this figure here, we have the black spectrum is the average stacked COS spectrum at redshift 0.2. And then we have the Muse spectra from redshift 3 to redshift 5. And what we can see is that there seems to be a decrease of the blue emission in these spectra as a function of redshift. And we then set up to try to confirm this. And what we do, it was take the black spectrum here and then attenuate it by the IGM relation from Intae et al. And then compare it to the Muse profiles. So the blue-green line here is the Muse profile stacked for this redshift. And the pink line is the attenuated cost profile. This is for redshift 3, redshift 3.5, 4, 4.5, and 5. And what we can see is that they overlap almost perfectly throughout these this redshift range. So what we can quite clearly say is that the imprint of the IGM can be seen here, and that there doesn't seem to be any need for an evolution in the intrinsic profile, which is very interesting. So just to summarize what we've done, well, we've shown that it's possible to predict Lyman Alpha emission well enough that it could be used as a model for intrinsic emission at high redshift, and that this may allow us to map the IGM during the late stages of ER. And we also shown that existing Muse spectra across a large redshift range seem to show the evolution of IGM neutral fraction through the attenuation of the blue peak. Thank you very much.
Thank you, Axel. So do we have any questions, please? You can post them on Slack. Okay, so we have a question from Hakeem Atek, who asks that, do you worry that your model, which is calibrated at low redshift, might not work so well at high redshift because of the redshift evolution of many galaxy properties?
Well, there is always a worry, but the fact that we use these galaxy properties in the model means that we sort of take at least some of this evolution into account. I mean, sure, if the properties evolve outside the parameter space that we probe entirely, then it might be difficult. But as long as they stay within that, we should be more okay than something that doesn't take all of these extra properties into account, is at least the hope.
Okay. And then we have another question from James Rhodes, who asks that compared to the Yang et al. Work, which predicted Lyman alpha strength based on the reg peak velocity, offset, and extinction, which physical or observational parameters give the greatest increase in predictive power in your model?
Yeah, so this is a big part of the work. I was just not, I didn't have time to present it, but we do look at which parameters give the biggest predictive power. And if we look at observable data sets, the far UV, so the UV continuum level essentially is definitely the biggest predictor, followed by the compactness of the galaxy. Whereas if we look at the model based on physical properties or derived properties, the star formation rate and the dust seem to dominate that relation. So.
Okay. Thanks. So we have a question from Crystal Martin, who asks, does your model take circumgalactic gas into account in any way?
Well, not explicitly that we put it into our model, but there is circumgalactic gas in the galaxies that we use to derive the model. So in that way, that contribution is in there, just by virtue of the data itself.
And a question from Intae Jung, who says, great study. Have you ever looked at any redshift evolution of your predicted Lyman alpha emission from galaxies?
No, we would need to collect data, quite a broad data set for galaxies across large redshift range in order to do that. And I don't think there's any data sets that we can just use as yet anyway. So no, we have not looked at that yet. It would be very interesting though.
Okay, this is an anonymous question. How can you explain the double peaked Lyman alpha emission in Cola 1?
I don't I don't have any specifics on the double peaked emission line in Kola 1, but I mean, I think there was work by Jorrit Mathey and by Gronke and you, Charlotte Mason, that looked at modeling this and the size of the new ionized bubble you would need around. So essentially the idea is that you have a big ionized bubble that allows the blue peak to redshift before it's removed entirely. But I haven't looked specifically at any galaxy like Kola 1.
Yeah, I mean, I think it's not an average sightline. I think it's
no, exactly. It's a very non-average sightline.
Yeah. Oh, okay, my very loud alarm. So thanks, Axel. That's time up for your questions. There's still several more to answer on Slack. Yeah. So please go and take a look there. Okay, so our next speaker is Lucia Perez, who is going to tell us about probing Patchy reionization with the void probability function in the era of the Roman Space Telescope.
Yeah,
take it away. Thank you.
Awesome, thank you. My name is Lucia Perez. I'm a rising 5th-year PhD student at Arizona State University, and recently I've been working out of Goddard Space Flight Center in Maryland because my advisors Sangita Malhotra and James Rhodes are on the Roman Space Telescope science team. And today I want to talk about my most recent project, in which I want to share with you different ways of probing patchy reionization using a clustering measurement called the void probability function, and make predictions for the Logger narrowband survey and also for Roman Space Telescope. So as we've talked about this entire time, some of the big questions that still remain about the epoch of reionization are exactly when it occurred, what was causing it, and always trying to find new ways to study it and really pin it down. So as we just heard from Axel, Lyman Alpha emitters are a really good probe of reionization because for most of these galaxies, the most prominent emission line is the resonant line of hydrogen. They're very unique and sensitive tracers of any neutral hydrogen in the intergalactic medium around them. So the Logger team, which is a really good collaboration who you can see at the bottom of the screen, that works between China, Chile, and the United States. A lot of the great work we're doing to specifically tie down reionization and ionization fractions is using luminosity functions. So as the emission from these galaxies is attenuated by the neutral hydrogen, the luminosity function drops and changes shape. And that's a really strong signal. So I want to show you that using clustering, you can measure that signal too in a different way using different model assumptions, and also get a unique signal that comes specifically from the process of reionization itself. Also, I want to hype up Roman Space Telescope. Its field of view is going to be so much larger than anything in space at these wavelengths. And the GRISM specifically will cover Lyman Alpha between redshift 7 and 14. And because it's going to have such a deep volume and large area, it's going to be great for doing clustering studies. So I'm really glad I went right after Axel because I'm using the Jensen et al. 2014 and 2013 simulations to do this study of how the void probability function can do this work. And thanks to the team, I know some of you are here who have shared your simulations with our team. But these are simulations of 600 co-moving megaparsecs on each side that have been evolved through reionization. And depending on the ionization fraction, they have at least 1 million Lyman alpha emitters within them. And I can give more details about this, but I'm going to focus specifically on how we can use these simulations to measure clustering and get an idea of the true value given our knowledge and assumptions, and also get a sense of any fundamental external errors that might exist. So what I do with these simulations is I make little experiments. So first, we can cut up the large volume into little slices that mimic what Logger will see. So the narrowband survey using DECAM on Cerrotololo sees 3.3 square degrees and a single viewing, and the narrowband covers about 30 co-moving megaparsecs in redshift space. So we can get 320 little slices to mimic a single Logger field. And then for the Roman Space Telescope, based on work that's being done by Isaac Wald with simulations, based on the fundamental limit that we think the GRISM will have, we imagine first just a square degree in the sky between redshift maybe 7 and 8 with a redshift depth of 0.5, which ends up really conveniently being little cubes of 150 co-moving megaparsecs on each side. So we can get 64 little test volumes to get a sense of what individual Roman space telescope fields might be able to do with this measurement. So my clustering method of choice is the void probability function. It's a really simple measure of clustering. You just ask if you drop a random sphere for 3 dimensions or a circle for 2 of a given size, how likely is it to be empty in your distribution? The VPF is really sensitive to number density, and we know the VPF of random distributions theoretically. And part of the work I was doing for the first couple of years of my grad program in a paper that's in the final stages of review is thinking about how we can use the logic of the VPF to get a sense of when your clustering measurements can be trusted, and also to make predictions. You might need this many galaxies in this kind of volume to get that measurement. So keep an eye out for that in the next couple months. So I alluded before that there are 2 different ways that clustering carries the signature of reionization with Lyman Alpha emitters. So the first way I'm kind of clumsily calling the single luminosity cut method. So we imagine a detector that has a fundamental limit for what it can see. So as you're detecting Lyman Alpha emitters farther back in time in more neutral IGM, you see fewer because it's getting more neutral. So we see this as we compare 95, 50, and 30% ionized. And you can see that at 30% ionized, the most neutral, the number density has dropped a lot and they appear more clustered. And this is a really strong signal. The luminosity functions that Isaac Waldo is going to publish soon are showing this really clearly. And even Wade Hu saw it in 2013 with the logger 2 fields. It's a really strong signal, and we'll see this very clearly with the void probability function. But this signal includes not only the effect of reionization, but also that maybe dark matter halos are merging themselves. But the second method we can do is taking advantage of the fact that we think that reionization is an inside-out patchy process. So Lyman Alpha emitters are more likely to be observed where the intergalactic medium has already been ionized. So if you imagine 2 distributions at different different ionization fractions, but you hold them to the same number density, the more neutral one will appear more clustered. So you can see this as I flip between 95 and 30% ionized. And this is a really subtle signal that, again, is a signature of patchy inside-out reionization. And I'm going to say that if we're ambitious, Roman Space Telescope will clearly be able to tell the 2 ionization fractions apart and give a completely different constraint for reionization. So let's do the measurements on these simulations. So the VPF, again, is a fraction that you measure at a given radius. So on these plots, the dashed lines are the VPF of a random distribution at that given density. And here we see what happens when you have a single luminosity cut that leads to different number densities. And the dots are the measurements of the VPF for the different ionization fraction versions of the same volume. And as you can see, each of the lines is really separated out from its own random distribution, which is great and expected. And they're really separated out from each other, even when you have some errors thrown in there. So again, we'll go into more detail of how we can see this with logger and WFIRST. But let's look at also next, the single density cut. Again, this is the really ambitious measurement that's a totally different way to measure inside-out patchy reionization uniquely. And as you can see, even when we use the whole breadth of our volumes, they're still going to be kind of hard to tell apart. So to explore how viable both of these measurements will be and to make predictions for these telescopes, let's zoom into a single radius first. The VPF is a volume average correlation function, so you can kind of take one radius and run with it. So first prediction, can logger measure the ionized IGM fraction with its 4 fields? So if you remember it, I cut up the volume into 300 little slices to mimic what a single logger field sees. So what we can do is I randomly choose 4 of these slices. I measure the VPF of each of them and then average that value together, with the hope that as you sample more of the larger volume, you get closer to the true population mean. And I repeat this process tons of times, so then we can see how the average of those 4 changes as you vary this. And as you can see with the single luminosity cut here on the left side, the 95 and 30% ionized have distributions that are really separated. So we'll be able to complement and constrain and help out the luminosity function analysis that our team is doing with the clustering measurement of the Lyman Alpha emitters once that becomes available. And then we can see with the single density cut, I warned you, this is a really ambitious measurement, and it might be rough to do from the ground. And even though luminosity cut is incredible, it's a different way of constraining it. Let's be ambitious and think about how can we get that signature of patchy reionization done. Let's look at the Roman Space Telescope. So how does 1 square degree do? again, we see that with the single luminosity cut, the distributions are quite separate. The binning isn't the neatest here, but it's okay. And again, with the single density cut, it might be hard with 1 square degree. So you can ask me, how many square degrees does Roman Space Telescope need to do this really difficult measurement? And the answer is 4. So you can see with 4 square degrees, the 95 and 30% ionized become really separated. And of course, this is a very ambitious measurement. The luminosity functions cuts, but the single luminosity cut will already be quite ambitious and do a great job. Thank you all so much for listening. Again, clustering can be a different way to complement our different methods of measuring ionization fractions. Yeah, thank you so much.
Thank you very much, Lucia. So we've got time now for questions.
And something I can say while these roll in, when the VPF of your given sample is measured, as long as it has very similar luminosity cut or number density, you can directly plot it on this and get an estimate for the ionization fraction based on the Jensen et al. 2014 simulations and their assumptions. Oh, great. I'm sorry, I have the Slack open right now. Do you want to read
those things are popping up? Yeah, so actually this is one question that I had as well. So from Fred Davies, how does the void probability function compare to using the angular correlation function in terms of how well reionization can be constrained?
That's a great question. So no one else has done the VPF with reionization yet, so I won't be able to answer that question until we get it done with observations. In terms of the theoretical side, the Quinn et al. 2007 made predictions for the angular correlation function. And it will do it well, like all the clustering methods will carry this signal with it. So that's still a question that's open of how well they can do. The other thing to consider is that samples of Lyman Alpha emitters above redshift 6 are very hard won and like really carefully tended. And especially with clustering analyses, you need a lot of galaxies. So this is something that only now is really becoming viable to do with like really, really good error bars. And I know that like a lot of teams have done really good work in constraining this. I know, oh my goodness, the name, it's a K-name 2006. They did the VPF of Lyman Alpha emitters at redshift 6.6, and that had a constraint, but they only had like 47 Lyman Alpha emitters because it was 2006. So it's an ongoing process. Good question.
Yeah, non-detections there. more of the what we're looking for with Lyman Alpha emitters at these redshifts. Okay, so there's a question from Steve Finkelstein who says, who asks, how deep do you need to go in line flux over this 4 square degrees for this measurement? Could you go deeper over a smaller region and get the same distinction?
Oh, excellent question. So the line flux limit I used is one that Isaac Wald recommended to me based on his WFIRST simulations, and that's 10 to the negative 17 ergs per second. And for the single number density, we ran with just what Logger is observing right now and also corresponds to what the WFIRST simulations are seeing. I think, yes, you can go deeper over a smaller region, for sure. Because the VPF like clustering measurements in general, like if you can get really, really good dense measurements, then that decreases your error. So for sure, I'm not sure exactly how much, but that's a really great question we can explore. Thank you.
Okay, and then a question from Fahad Nazir, which is, I guess, a bit related to Fred's question, but have you tried methods other than the void probability function?
I personally have not, but Jensen et al. In their 2014 paper do this with count in cells, and they show that difference. But I will say that they specifically focus on the single number density cut method when they showed their count in cells, but it would be a very, very strong signal with the single luminosity cut too.
Okay, and then I can't see more right now. So I actually have a question too. I guess, I don't know if I missed this right at the beginning, but could you talk a bit more about the model that you use for the Lyman Alpha emitters themselves and whether that like evolves with Redshift?
Yeah, so this was a lot of great work that this whole team did for several years. So I have some summaries here. I have slides that can tell you a lot more. If I remember correctly, and feel free to correct me in the chat for those who worked on this, I think if I recall correctly, they had like a single shape. I'm sorry, this is like a little like rough in my memory. I think the biggest thing with the line, I don't want to speak too much and be wrong because like this was a lot of really careful work they did. But yeah, the biggest thing was that they simulated the observed Lyman Alpha emission as it emerged from the galaxy and then as a separate step as it went through the IGM. So I will leave this here so then folks on the YouTube can read my summary of this and pause on it. But that's a great question. Yeah.
Okay, thanks, Lucia. Yeah, that's we're gonna have to move on now. So hopefully we can have more discussion of this via Slack. So the next talk is from Intae Jung, who's going to tell us about the Lyman Alpha equivalent width distribution and ionized structures at redshifts greater than 7.
Hello.
You can share your slides now, Intae.
Hello, do you hear me?
Yeah, you can share your slides.
Yeah. Hello, my name is Intae Jung. I'm a postdoc at NASA Goddard.
We can't see your slides.
Oh.
There you go. Like we can see them.
Hello. Do you see my screen?
Yes.
Okay, yeah. My name is Intae Jung. I'm a postdoc at NASA Goddard. Today, I'm going to talk about the Lyman Alpha equivalent width distribution and ionized structures into the epoch of reionization at redshifts above 7. This talk is based on my recent paper, which is extended from my PhD study with Steve Finkelstein, and it has been submitted to HA a month ago, so it'll be available soon on arXiv. So here I have my collaborators. So this week, we had a great discussion about the Lyman Alpha emission as well as reionization. So that's because Lyman Alpha visibility is one of the most promising probe of reionization. So such as the measuring the Lyman Alpha fraction or looking at the Lyman Alpha luminosity function. So along with those studies, here we implement a more detailed analysis of Lyman Alpha on constraining the equivalent width distribution. The motivation of studying the equivalent width distribution is that it uses more information from spectroscopic observations than the others. For instance, the Lyman Alpha flux, galaxy UV continuum level, in addition to the number of Lyman Alpha detections. The equivalent width distribution has been studied at various redshift ranges, and it's well described with an exponentially decaying functional form, which is shown in the left plot, and that are characterized by its e-folding scale W0. The redshift dependency of the equivalent width distribution, so its e-folding scale is shown in the right plot from Santos et al. 2020, which displays the compilation of the distribution measurements at redshift from 0 to 6. At redshifts below 6, where reionization has been completed, the folding scale does not change very much over time. However, into the epoch of reionization, an increasing amount of neutral hydrogen in intergalactic medium would have an impact on the Lyman Alpha visibility. So here we aim to constrain the equivalent width distribution at reionization epoch in order to trace the evolution of IGM neutral fraction. So searching for Lyman Alpha emission at around the end of reionization, we performed a deep spectroscopic follow observations for nearly 200 high redshift candidate galaxies with Deimos and MOSFIRE. This plot shows the entire survey program in the Goose field. Today I'm presenting the result from the entire MOSFIRE observations in the Goose South, Goose North, as shown in the yellow rectangles. And the rest of the survey has been published in the other publications. So these MOSFIRE observations targeted around 70 redshift 7 candidate galaxies with six different mask designs for 10 nights of observations in total. See, although our MOSFIRE observations provide the deepest near-infrared data set for Lyman Alpha at these redshifts, it's yet very challenging to detect emission lines from these faint and distant sources. So in order to help detecting faint emission lines from those noisy spectra, we applied an improved manner of automated emission line search on our reduced spectra. After the detailed data reduction correcting the non-slate drift issue of Moss fire, we specifically performed on automatic scanning on both 1D and 2D spectra. Our automatic scanning has been done with source extractor runs on 2D spectra and 1D Gaussian fitting search on 1D spectra. So in short, this automatic scanning detected several emission lines missed from visual inspection, which supplements that visual inspection and guarantees the machine-driven consistency on detecting the faint emission lines. So we also checked all low redshift possibility and finalized the list of Lyman Alpha emitters. So finally, we detect Lyman Alpha emission lines from 15 galaxies in total from 70 galaxies, and 10 of them are detected at 4 sigma level displayed in the left and listed in the top rows in the table in order of their spectroscopic redshifts. So we perform asymmetric Gaussian fitting on reduced 1D spectra to estimate the physical properties of the detected Lyman Alpha emission lines that are listed in the table, including emission line fluxes and equivalent width and the line asymmetry. So these are the great number of spectroscopic confirmations ever at these redshifts. And before I move on the estimating equivalent width distribution, I am giving a quick summary of our findings from the Lyman Alpha emission properties. So we detect 10 emission lines, 10 Lyman Alpha emission lines at redshift above 7, including one at redshift 7.94 at the highest redshifts among these. And we find 6 Lyman Alpha emitters with equivalent width larger than 50 angstrom, including one extremely large equivalent with Lyman Alpha emitters of 280 angstrom. So this proves that these large equivalent with Lyman Alpha emitters are not very rare in this early universe. And also we couldn't find any agent signatures from our observation, so that this may require very young and matter poor population stars to explain its extremely large equivalent width. We also estimate the asymmetry of the line profile, which reveals that most of these Lyman Alpha shows asymmetric shapes. And also with the largest number of spectroscopic confirmations at redshifts above 7, we tested the accuracy of the photometric redshifts, measuring the relative errors in the right bottom pattern. So our result shows the overall quality of our photometric redshifts measured from Finkelstein et al. 2015, obtained from HSD and speech IROC data appears really good. With these successful detections of Lyman Alpha emissions, we measured the equivalent width distribution of Lyman Alpha at these redshifts. So here we applied our methodology from Jung et al. 2018 for constraining the distribution by assessing the likelihood of detecting Lyman Alpha emission lines from simulated mock emission lines. This is because this methodology utilized both detections and non-detections, putting more constraint on the equivalent width distribution. And this method considers all data incompleteness that are affecting the Lyman Alpha visibility in our observations, such as photometric redshifts and galaxy continuum level and observational detection limits. So I'm skipping the details of the method, but in short, we basically obtained the probability distribution of the expected number of detections with the folding scale from 5 to 200 angstrom, as shown in this plot. And we fit this simulated template to our actually detected Lyman Alpha emissions to find the best fit value of e-folding scale of the distribution shown in the right panel. So our best fit value of e-folding scale at these redshifts is 32 angstrom. At the bottom, compared to those values at lower redshifts, our measurement at redshift 7.6 shows a reduced e-folding scale which implies an increasing H1 fraction in the IgM. So with the measured equivalent width distribution, here we also infer the IgM neutral fraction. So in order to do that, we estimate the Lyman alpha transmission in the IgM. So that reflects the optical depth of Lyman alpha in the IgM in radiative equation. And that can be empirically derived with some simplified assumptions. So briefly, we consider the intrinsic value as emitted from the galaxy, but not affected by the IgM. And the observed value reflect the IgM attenuation. So we take the intrinsic equivalent width from redshift below 6 in the ionized universe, as shown in the table. This assumes no critical evolution of the ISM and CGM properties between these two different redshift ranges, although further studies are absolutely necessary for understanding them. And we adapt an analytic approach to estimate the H1 fraction as below, which relate Lyman alpha transmission to the average H1 fraction. So our inferred H1 fraction is around the 36% at redshift 7.6, which is considerably lower than the other recent studies reporting the value from 55% up to 88% at similar redshifts. So we find that this may prove an intrinsic inhomogeneous nature of reionization. So relating to such large variation, the IgM topology matters here again, reionization is an inhomogeneous process. So in the same context, we study spatial clustering of Lyman alpha emitters shown at the bottom. The left panel presents the number of detected Lyman alpha emitters through the line of sight direction and to the spatial distribution on the right. So the notable feature is the peak near redshift around 7.5 to 6, where we detect more number of Lyman alpha emitters than expected. The blue dots on the right are the clustered Lyman alpha emitters, which forms two pairs of Lyman alpha emitters. So these results indicate the presence of large, highly ionized structure with a spatial extent of 40 cubic megaparsec containing these two locally ionized bubbles. So all of these findings provide evidence of inhomogeneity of reionization. And I will stop here and take your questions. Thank you.
Thank you very much, Intae. So start looking at some questions on Slack. So we have a question from Christopher, I do not know who's the last name, who asks, are your equivalent widths rest frame?
Yes. So that are all measured in rest frame.
Okay.
Yeah.
Okay, so a question from Ryan Ensley, who says, very interesting work. Maybe I missed it, but do you find a difference in the e-folding scale at redshift greater than 7 for bright versus faint galaxies, or at least in their evolution from lower redshifts?
Oh, yeah, I didn't mention about that, but we do see some evolution of the equivalent width depending on the galaxy continuum brightness. So it's interesting to look at the evolution at different UV magnetic ranges. So particularly what we found from our observation, we do actually see an increased value of equivalent width at the brightest galaxy bins.
A question from Takahiro Morishita, who says, nice talk. Is there a possibility that the largest equivalent width object is an AGN? What is its absolute magnitude?
Oh, yeah, so we want to check it if it's AGN, but we do not see any AGN features like nitrogen 5 emission, and all of the targeted galaxies are free from the X-ray sources. So it might not be AGN. Yeah.
Okay. So a couple of questions here. So sort of merging a question from Rohan Naidu and Brian Lamo. Basically asking whether you account for the fact that these sources could be in an overdensity when you calculate the neutral fraction.
When I calculate the neutral fraction, we include all of these orbital density, and also we test our value by removing those orbital density regions. So removing those 4 clustered Lyman Alpha emitters. So that would improve the measured neutral hydrogen fraction by around 10 to 15% more. So it's more comparable to the other studies. In case we disregard those orbital density regions.
All right, thanks, Intae. So I think we've got to move on, but there's lots more questions on Slack for you to have a look at.
Okay, thank you.
Okay, so there's going to be a small change to the schedule now. So Michaela Bagley is having some internet issues, and hopefully will be able to join us at the end of the session, but we're just going to move the next 2 talks up. So the next talk is going to be from Huanqing Chen, who's going to tell us about what we can learn from quasar proximity zones. So you can start sharing now, Huanqing.
Can you see my screen and hear me?
Yes.
Okay, cool. Thanks for the organizers. I'm Huanqing Chen from Chicago. I work with Nick Nieding on reionization simulation. And today I'd like to talk about what can we learn from quasar proximity zooms during reionization. As the name suggests, the quasar proximity zone is a region just surrounding a quasar where the radiation field is dominated by the quasar. Depending on the luminosity, this proximity zone can extend to up to 10 physical megparsec. That is including a lot of large-scale filaments and halos. And because of the nearby quasar, this region experienced quite a different reionization history than the common field. So studying this region, especially the gases in this region, can help us understand how different reionization history impact the gas formation. And this is one of the big reasons that why the quasar proximity zones are so interesting. So another big reasons that we love the proximity zone is that this region can potentially help us constrain IgM properties, because we know that the size of the ionized bubble depends on the total number of ionizing photons and neutral atoms. So by measuring the proximity zone size, we can potentially constrain the IgM density, neutral fraction, as well as the quasar lifetime. The way to measure the proximity zone size is to look at their spectra. So here I show an example from Eiler's paper. And this is a pretty typical reionization epoch quasar. Although at the redshift 6, the universe is pretty already ionized, but because of the large cross-section of the Lyman alpha photons, as long as there is some trace of neutral hydrogen, we will still see the saturated absorption. And this is the Gamma-Petersen trough usually observed in Z-about 6 quasars. But thanks to the high flux of the quasar, the region surrounding it will have an exceptionally low neutral fraction. And this will appear in the spectra as this non-zero flux region. And this is a place that we can do a lot of interesting work on. And in the future, we will expect more and more high resolution spectra being taken from this reionization epoch quasars. And this motivates us to analyze this region in more detail. So in this project, we study proximity zone using the synthetic spectra. We obtain this synthetic spectra by post-processing cosmic reionization on computer simulation. This Krog simulation has both a relatively big box of 60 comoving megparsec, as well as high spatial resolution, and allows us to resolve the Lyman limit system, which is potentially important in modeling the proximity zone. And the simulation include gas cooling, heating, star formation, stellar feedback, and the radiative transfer is also done on the fly and allow us to model realistically the gas neutral fraction as shown in the right figure. The simulation itself doesn't include individual quasar sources. So we obtain the quasar spectrum by first identify a bunch of big halos, massive halos, and then draw sidelines centered on these massive halos, and then post-process them with 1D radiative transfer code. Just to show you some example, this is a sideline drawn from Redshift 8. The upper panel is the neutral fraction, lower panel, the transmitted flux. And the black line shows the value before we turn on the quasar. So at Redshift 8 in our simulation box, most of the IgM is still neutral, except for some bubbles surrounding big galaxies. And right after we turn on the quasar, after 1,000 years, the value become like what plot in the blue. So immediately the neutral fraction drops to -7 and 10 to -7, and then proximity zone appears in the spectra. And the dashed line here I show is a smooth spectra, and this is what in practice measurement is usually done. It's usually defined as the point where the transmitted flux drop below 10%. So now I will click through to show you how this proximity zone evolve as the quasar shine longer and longer. So we can find that in a time scale of 10 million years, this proximity zone will grow to a larger value. And this is the case for the high redshift before global reionization. The picture will look pretty different if we look at the case after global reionization, for example, at the redshift 6. At that redshift, since the universe is already pretty ionized most of the place, so there will be no more such typical quasar I front, but the whole universe has dropped to the IgM has dropped to the value of 10 to the -3. And so the time scale for the quasar proximity zone to grow is set rather by the time scale for the IgM to reach a new ionization equilibrium. So I put them side by side to show for you to compare how this proximity zone evolve. As you can see that within a 0.1 million years, the proximity zone size already grow to a large value. And afterward, this doesn't change much since the ionization equilibrium is established almostly. So to summarize what I just showed, here I plot the proximity zone size as a function of quasar lifetime. So before reionization at the redshift like 8, the proximity zone grows steadily in the first 30 million years. But after global reionization, this proximity zone will only increase significantly in the first 0.1 million years. And this arrow bars here I show covers 68% of the silines in our sample. And we can see that at the redshift 6, where most observations are taken, most of the old quasars have a zoom size around 4 physical megaparsec. Interestingly, in observation, Ilas et al. 2017 has measured some quasar sideline that has very small proximity zones. And I encourage everybody to listen to her talk tomorrow. So how to explain the small proximity zone is always a challenge. One possibility is always that the quasar is very young, but this is not very desirable for a supermassive black hole to grow to such a massive value within the 1 gig year of the universe. So in my last slide, I'd rather show you how old quasars can have those small proximity zones. So we search for our Redshift 6 quasar samples, and we find that 2% of the old quasars have an extremely small proximity zone that is more than 1 physical map parsec. And if we look closely, we can find that most of them shoot through a gas that has overdensity above 100. And then this dense and neutral clump of gas will shield the gas behind it. And most of the time, they will show up as damping wing in the spectrum. And if we plot the over density of this cloud in the histogram, it will look like the right figure. And most of them hit the gas with the over density above 1,000 within the 5 physical map parsec. So here I show my conclusions. In a neutral universe, the proximity zone size will increase significantly in the first 30 million years. But after global ionization, the proximity zone size will only significantly increase in the first 0.1 million years. In our simulation at Redshift 6, 2% of the quasar has a very small proximity zooms, and most of it because the Lyman limit system or Lyman Alpha system on the way. And thank you. And I'm happy to take any questions.
Okay, thank you very much, Huanqing. So we've got some questions coming in on Slack. Okay, so let's start with a question from Hamza Padamanbam, who says, thanks, very interesting talk. Do you consider a duty cycle for the active lifetime of the quasar in your work? I thought it might be interesting.
Yeah, right. So in our work, right now I only just use the light bulb model, just light up it, and then the result here is for the we have not turn off and turn on, but I think previously Fred has did some work on the flickering model. Yeah, it will be interesting, and I will look at more into it. Yeah, thanks.
Okay, and then a question from Enrico Garaldi, who asks, is the dense gas associated to the quasar host, something like a merger?
No, these are very far away from the quasar. So here is already at more than 1 physical map parsec, which is not possibly associated with the quasar host.
And then a question from Garrett, who says, nice talk. How do you deal with the light travel time effects, the speed of light in the growth of your quasar near zones? How do you make sure they don't grow superluminally?
In this particular observation, the speed of light is kind of cancel out. So here I probably show you a schematic of this. So the light here I show skyline and the time. So if we assume this is the speed of light, then what we actually observe is the regions between this. So assume this is the light from I from this is the speed of light. Then what we see is kind of the time, the real time minus the retarded time. So in this calculation, this factor is canceled out. So we don't need to worry about the line speed of light limitation.
Thanks. So we've got time for just one more question. So it's a question from Sarah Bozeman, who asks, how dependent are your results on the mean IgM neutral fraction evolution?
So in our simulation, this we kind of self-consistently model both the neutral fraction and the temperature. So we haven't looked into how varied reionization history affected, but we do have many boxes, and we can look into more boxes to see how this affected. So yes, good question.
Okay. Okay, thank you, Huanqing. So there's lots more questions on Slack for you to look at. And let's move on to our next speaker, who is Jinyi Yang, who's going to tell us about constraints on the IgM evolution using a new reionization quasar sample.
Thank you. I will just share the screen. So can you see my slide?
Yes.
Okay, thank you. Okay, so thanks for the opportunity. Today, I will present my recent works. Oh, yeah. First, I'm Jinyi Yang, postdoc at Stewart Observatory, University of Arizona. So today, I will present my recent work about using a new reionization-era quasar sample to constrain the IgM evolution. So first, this is a typical quasar spectral at redshift around 6. As we know, we can see a series of absorption features in the quasar spectra that providing us with information of the IgM at the early universe. And we can see, for example, the Lyman Alpha, Lyman Beta forest, and to high redshift, we can also see the Peterson trough. And we can also see the near zone just blueward of the Lyman Alpha emission line. As we know, if the neutral fraction is high enough, for example, to high redshift, we can also see the quasar damping wing absorption feature. Now we can see the Peterson absorption extended to the right side of the Lyman Alpha emission line. And this is a simulation, and we can also see the observation, the spectral. This is a real spectral of redshift 7.5 quasar. Currently, there are already 2 quasars at redshift above 7 have similar measurement. We can see the obvious absorption here. That's the quasar damping wing. So what I want to do, my work is based on a new quasar sample from our new redshift 7 quasar survey. So we have carried out a redshift 7 quasar survey and have already discovered more than 35 quasars at redshift 6.3 to redshift 7.6. We can see this distribution here. So all the red points are from our new survey. And more details will be shown in Figures talk tomorrow morning. So after we build up a large sample of the high redshift quasar, the reionization-era quasar sample. So what we want to do is to use this quasar sightline, high redshift quasar sightline, to investigate the IgM evolution at redshift above 6. So that including 2 projects. And the first one is using this quasar sightline to study the IgM optical depths at redshift 6 and above. So I'm using 32 quasar sightline, including quasars at redshift 6.3 to 7. And I'm taking a deep optical spectroscopy of these quasars, and we get this quasar spectral showing these 2 figures. We can see these two figures, and our quasars shown here with the name showing right from our new survey. So we can see our survey have already contributed a lot to the sample build-up. And based on these 32 sidelines, the first thing that I can measurement is the Lyman Alpha effective optical depth. So here, this figure show the this is a measurement from previous works and predictions of the Lyman Alpha effective depth evolution from redshift 4 to redshift around 6. So we can see these points over the lower limit. They're from individual, the measurement of the individual quasar sightline. And we can also see the blue open squares here. They're the mean measurement of the optical depth. And we can also see the these 2 lines, the green line. This is the best fit evolution model for redshift below 5.5, and also the prediction for high redshift evolution. So this is what we currently know. What I want to do is, since we already built a high redshift quasar sample, and using this high redshift sample to investigate, to constrain the Lyman Alpha effective optical depths at redshift higher than 5.8. Higher than 4.8. And based on our set line, this is what I obtained. This is the orange point here. Is the measurement of the Lyman Alpha effective optical depths from the individual sightlines. And we can see our sample at the redshift range of 5.3 to 6.5. Although at redshift higher than 6.1, more than half of them are just still a lower limit. So So based on the individual measurement, our result is consistent with the previous studies that about the large scatter of the optical depth at redshift about 5, which has already been suggested to related to the inhomogeneous reionization process. As I mentioned before, at redshift higher than 6.1, we can see where they have just lower limit. That's due to the high neutral fraction there, and also at this redshift range is also limited by the data quality. So to improve the signal-loss ratio of our data, and also to reduce the contamination from the skylines, so I did a stacking of the 1D transmitting spectrum. I just stacked over 1D spectrum from our sightlines and get a stacked spectrum and just measure the effective optical depth from the stacked one and get this the orange upper circles. This is the measurement here. And now we get a good measurement around redshift 6. And so we can see we have already improved the measurement at this redshift. And also based on this measurement from the stacked spectrum, and also combine the result from Ehlers 2018, and we get a best fit evolution model at redshift 5.3 to 6.1. This is a solid orange, this is a solid line here. And we can see this one is consistent is within uncertainty at the redshift about 5.8 with the prediction of the green line. But to higher redshift, we still can see a redshift higher than 6.1, we still just get the lower limit. This is affected by the high neutral fraction, where Lyman Alpha transition may be saturated. So in this case, we need an additional tracer. So that's why we use, I'm using the Lyman beta forest, which is more sensitive to the high neutral fraction IgM. So using Lyman beta forest, I'm using the same way to measure the effective optical depth from both individual and the stack spectra. I first measure the observe the Lyman beta effective depths, and then convert it the Lyman beta one to the Lyman alpha effective depths by subtraction the foreground Lyman alpha absorption, and also applying a conversion factor between Lyman alpha and Lyman beta, and just in order to compare our Lyman beta result with the Lyman alpha result. So we can see in these two figures. But this is the left one show the individual from the individual sideline, and the right panel show the result from the stacked spectrum. From both, so we can see the Lyman beta forest provide additional constraint on the Lyman alpha effective optical depths at redshift around 6 to 6.5. Especially we can see from the stacked spectra. So we can see there is a measurement, although with large uncertainty. So there's a measurement at redshift 6.2, and this is consistent with the best fit evolution model from our Lyman alpha measurement. And to high redshift, still large scatter and over the limit. That's maybe limit affected by the small sample size at the high redshift end, and also affected by the high redshift transmission spike. I will show it later. So here we still need a larger sample at high redshift to constrain the Lyman beta forest. In addition to the Lyman alpha and Lyman beta forest, I'm also using the high redshift transmission spikes from our site line. Just identify our high redshift transmission spikes. We built up a sample of more than 400 transmission spikes at redshift higher than 5.5 to redshift up to 6.3, including Lyman alpha and the Lyman beta transmission spikes, as shown in this figure. And since we already built a large sample, and we can do something statistical. And this is the bottom left one. This is number density evolution of this transmission spike. That's the number density along the sight line. So you can see the number density evolution over redshift, and also at different bins of the transmission spike strings. And we can see the rapid or the obvious rapid decline with increasing redshift, and also with increasing transmission spike strings. So this evolution may suggest that there is a very rapid last transition phase of the reionization. And again, use this transmission spike back to the Lyman alpha effective optical depth plot. We can also use these transmission spikes to constrain Lyman alpha optical depths. So by assuming that this transmission spikes can represent the overflux from this sight line, which means that other pixels just have the zero fluxes. So we treat these two values as upper limit of the Lyman alpha effective optical depths. You can see the open black squares here. There are the two upper limit from transmission spikes. you can see they have very good agreement with the best evolution model from the Lyman Alpha measurement. So this also can support that our transmission spec sample has a very high completeness. So the discovery of this transmission spike may suggest that a redshift around 6.2 to 6.3, the IgM may be already ionized. So there should be a rapid last transition phase of the reionization from redshift 7 to this redshift. And this is the first project using 3 different tracers to constrain the Lyman Alpha optical depths around redshift 6. And the next one is when we go to high redshift, when we want to go to redshift above 7, we can now see, we can now use the Lyman Alpha Lyman beta forest, and also it's hard to find transmission spike there. So what we can use is a quasar damping wing. As I showed before, there are already 2 quasars above redshift 7 have similar measurements. And these 2 quasars, these 2 new sightlines from our new survey is a redshift 7.5 quasar and a redshift 7 quasar. So we can see, interestingly, these 2 quasars give us very surprised result because there's a very weak damping wing feature at redshift 7.5, but a very strong damping wing absorption at redshift around 7. So actually the redshift 7.5 sightline, the weak damping wing feature, that is more weaker than all of the other 3 quasars at redshift above 7 that have similar measurements. So the weak damping wing features could result in very the discrepancy of the damping wing absorption features between these 2 sightlines result in the discrepancy of the neutral hydrogen fraction estimate. So in this figure, we can see this figure shows over the measurement of the neutral fraction from the high redshift quasars. So we can see including that's the low redshift one from the optical depths and all the dark gaps, and this 4 from 4 sightline for quasar sightline above redshift 7 as a damping wing measurement. So we can see from our 2 new sightlines, the orange point and also the red point. So then we get a high neutral fraction at redshift around 7 and a lower redshift neutral fraction at redshift around 7.5. So we can see, although they have the large uncertainty, but we can conclude that the discrepancy of the damping wing absorption features from these 4 quasar sightlines suggests that the reionization could be patchy. Okay, and this is a summary. Yeah, we used our new quasar sample, a new quasar sample at redshift 6.3 to redshift 7.5 to constrain the IgM evolution, and including to project. The first one is optical depth at redshift 6 and above, and the other one is the quasar damping wing at redshift higher than 7. Yeah, okay. I'll just leave it here and take questions. Thank you.
Thank you, Jinyi. So we've got questions on Slack already. So let me start with a question from Gabor Warszek, who asks, how do you combine sightlines of different data quality?
Sorry, say again.
How did you combine sightlines with different data quality?
It's just I combined the. Do you mean the stack spectral, the step of the stacking spectral?
I think.
I guess yes. Yeah. We just stack the transmission spec, and they're from the different resolution and they have different signals. But I think the different resolution will just skew over the spectral to the lowest one in this bin. And we just stack the histogram, stack the pixels within this bin, and get a stack of the 1D transmission spectral, and then get a stacked spectral of the over 1D transmission spectrals. Yeah, we are stacking the transmitted flux.
Yeah. So a question from Hamza Padmanabhan, who asks, in your effective optical depth plot, is the dotted line an extrapolation from the FAN 2006 results? If so, it seems to indicate a rapid evolution in tau effective. Has the scatter actually decreased with the new sample, comparing the left and right curves?
Do you mean the dotted line? I think I mean the dotted line here. I think, yeah, the dotted line is from the FAN 2006. Yeah. Yes. And if so, it seems to indicate a rapid evolution. With the left or right curves.
And whether the new sample,
Oh, I need to back into this one. I think
whether the scatter is decreased in the new sample.
I don't think the scatter is decreasing. Actually, as I mentioned before, the scatter redshift around 5.5 and to redshift around 6 is consistent with previous studies that there is a large scatter. And to high redshift, the scatter here is larger. But to high redshift, that may be affected by data quality. As we can see, there are around a lot of lower limits. Yeah. So the scatter is still large. It's not decreased.
Okay, thanks. And then just one final question from Fahad Nazir, who asks, how are you dealing with the continuum correction of these high redshifts, as these sightlines can be affected by variations and troughs?
I think you mean the continuum fitting of the intrinsic to get the intrinsic Quasar spectral. Currently, we only have the optical spectra. So this is a very high redshift Quasar sample. So we just typically just only have Lyman Alpha and negative 5 line. So we cannot do PCA. So I'm just using a power law. And the uncertainty of the power law fitting is around 10% to 15%. Yes, there is but actually, I did some comparison. Our result, for example, we know that Atlas 2018, they're using the PCA model. And I can show you also this one. That one may be more interesting. I just compare our result to the distribution of the Lyman Alpha effective depths, and to compare our result with previous studies. So we can see our result, the right line is consistent with the previous studies within uncertainty. Although some of the previous studies are using PCA, some of them are using the power law fitting. So that may be support that the power law uncertainty will not significantly change the result. Yeah.
Thank you. So it looks like, unfortunately, Michaela wasn't able to connect to this session. So Michaela Bagley is going to record her talk and it will be posted online. So please do check that out and ask questions in Slack. And we should be able to link, I guess we can link to it within the Slack channel for this session as well. So I think that means that we're pretty much wrapped up with today. I wanted to just make one announcement that we will host a follow-up discussion about equity and anti-racism. And I think based on the poll so far, we're going to make that session tomorrow, just before the start of the sessions tomorrow. So at 1300 UTC. And I will post about that on Slack as well. So unless there are any more things to mention from anyone else, Steve or Steve?
I think we're all set. Thank you, Charlotte.
Yeah. Okay, that's great. So let's end now and enjoy the rest of your days or nights, everybody. Goodbye.